I guess I will start just with who I am. I think I know a lot of people in the room. I'm actually surprised. Some people I know are here that I know who are here that I wasn't expecting to see here. So that's great. I have a few different hats that I wear that I think are kind of relevant to this audience and to this workshop. My kind of day job is as the NERSC Application Performance Group Lead. So we started this group, I guess back in 2016, so about 7 years ago, and I can kind of tell you why we started this group over the course of the talk. But this is the group that engages with application teams, not just in the material science and chemistry and physics area, but in kind of all different areas, including like climate science and fusion and QCD and a bunch of different science areas. I also lead the program called NESAP, which stands for the NERSC Exascale Science Application Program. And so this is a program that we launch every time we bring in a new system to partner with application teams. We usually partner with about 20 application teams to work with them kind of hand in hand to prepare their applications for the upcoming system. I am also so my PhD was in condensed matter physics, condensed matter theory, and so I continue to work with the group that I worked with as a PhD student at UC Berkeley to work on this code called Berkeley GW. And so one of the reasons why I went into like HPC after graduation is that during my PhD I kind of spent a lot of time working on this code Berkeley GW and kind of preparing it for the latest and greatest HPC systems at the time, and I kind of discovered I really liked that process. So that's sort of how I ended up at NERSC. And then maybe the final hat that is relevant to this audience is I am the ECP sort of L3 or the area lead for the material science and chemistry area, which contains 6 applications you can see written here, including some that you've heard a lot about this week, the lamps or what they call the XALT project in ECP, as well as a number of others. One maybe doesn't quite fit, which is QCD, and I think they just lumped that in maybe because it also deals with small things. I'm not really a QCD expert, but it's just part of the portfolio that I manage. I'm not quite sure which one of these hats is like the leprechaun hat, but I thought it was appropriate for St. Patrick's Day. Okay, so I'm going to kind of tell you about kind of NERSC philosophy for measuring performance and kind of preparing applications for Exascale. And I think this is sort of maybe half like a presentation where we kind of show off some of the accomplishments, but the other half is more of like a tutorial on in a tutorial spirit where you can kind of copy and like run some of the same commands that we ran in order to mimic the results with your own application. And so the spirit of all of this is that the DOE is on a path towards Exascale where the architectures are changing. And in particular, as we're looking towards the near future at least, what Exascale kind of means to the Department of Energy is GPU accelerators. And interestingly, there's still some diversity among the type of GPUs that are being deployed. At NERSC, we just deployed Perlmutter, which is based on what was when it was deployed the latest GPUs from NVIDIA, the A100s. The H100s are just about to kind of hit the streets. At the ALCF, there's the Aurora system with the Intel GPUs. And of course, at Oak Ridge, there's the Frontier system with the AMD MI 250 GPUs. And throughout the talk, I'm going to sort of use Berkeley GW because it's an application that I sort of worked on, and it's kind of near and dear to my heart as an example success story of what the tools and this approach to performance optimization can do. And so just a brief introduction to Berkeley GW as this kind of example success story. How many people know what the GW method is? Does everybody know? So maybe about half the room. So GW is a many-body perturbation theory method based on Green's function approach. That's what the G stands for. It turns out W actually just stands for W. It's like this, like V is the symbol for like the Coulomb potential, right? And W is a symbol that's used for the screened Coulomb potential. So if you add in the screening of like electrons, for example, in a semiconductor or metal, we use the symbol W. So W just really stands for W. But it is a way to kind of correct DFT excited state properties. So DFT is formally a ground state theory. GW sort of corrects the energetics that you get in excited state. So what happens if you sort of shine light on a material and you create an electron in a hole, it gets those energies right, whereas DFT is known to have this like band gap problem, right, where it sort of systematically underestimates the band gap. But this is not really a talk about necessarily GW. It's just this is an application that I think is in this space and is we can kind of talk through the optimizations that were made for this application. So I think this is a story that could be told about a lot of applications in the material science and chemistry space, but this is sort of like the scale of these calculations over time. So GW calculations had kind of been known for being very, very accurate, but also very, very expensive and hard to scale. And that was something that kind of a collaboration between the Lawrence Berkeley Lab and UC Berkeley campus had kind of tried to address through the application of like HPC best practices and targeting like leadership class systems. And so if you look at the scale of these calculations over time, it's kind of going up in the Moore's law type way, exponential type way. And just recently we've been, doing calculations on the order of tens of thousands of electrons, which is sort of the biggest that had ever been done at the time. And so here's an example of why you might want to consider a system with 10,000 plus electrons. This is a silicon carbide supercell with a dye vacancy defect, which is sort of like a prototype system that the defect states could be potentially harnessed for quantum computers. And so, you have to end up with this large supercell calculation in order to fully capture those defect states. In terms of the value that GPUs provide, I think this plot here shows kind of immediately the benefit, and that is in the energy to solution. So you can basically calculate the energy used, or like the power used, times the wall time of a calculation to get the total energy to solution. And you can see that if we compare two systems from the same generation, so Cori, so that's one system back at NERSC, and Summit, which is one sort of system back at OLCF, there's an order of magnitude difference when you're using the GPUs in terms of this overall energy to solution. We have it in units of, I guess, kilojoules, but it could be watts, right? Or watt hours. And that's essentially, in a nutshell, why HPC centers like NERSC, like OLCF, are moving to GPUs, is because of this order of magnitude difference between a CPU calculation and a GPU calculation in terms of the capability that can be provided for the same energy envelope. And then, of course, you can see that this is also reflected in time to solution. for the same calculation as well.
I find this very surprising. Can you say a bit more why this is? Like, what is it just a difference in instruction set that allows us to be more power and more power efficient, or?
Yeah. So let me just hop ahead for a second. This is maybe the analogy that might make sense. Is that like the CPU is like this sports car that it can do everything kind of really fast, where like it can get you from one destination to another really fast for like kind of for a single passenger, but the GPU is like this double-decker bus, right? Where it can get a lot of data somewhere to a destination slower than the CPU can, but more efficient, but sort of more efficiently. And the reason why it is, partly due to like the instruction set, like the GPU instruction set is very simple. You're forced to do the same operation on a lot of data at the same time, whereas the CPU, you can kind of it's more latency optimized. You can kind of context switch faster and move between like doing different operations on different streams faster. But the GPU is essentially just a big vector processor from the, almost an analogy to like the old vector processors that, Cray was famous for before we made this transition is the short answer. So you're kind of limited in the independence of what each thread can do on a GPU, and that gives you the energy efficiency. Okay, so so here's been our path towards Exascale for Berkeley GW. We started with like an OpenMP multi-core implementation for Cori. We'd made a CUDA implementation, and now we're thinking about these performance portable implementations using OpenACC and OpenMP, which I think maybe Rahul and others talked a little bit about yesterday. And this is just kind of one interesting slide about those that I thought I would throw up here because I know Rahul had talked about it yesterday, is like what level of performance do you necessarily give up when you go from something like CUDA, where you're very explicitly programming the GPU, compared to something like OpenACC and OpenMP, where you're doing something at a higher level more portably. And you can see we've been able to get close in some cases. Probably the biggest difference or the biggest like ratio is in this particular kernel. But I think that there is some optimism among our team that these numbers are good enough and getting better, especially when you compare them to like the CPU-only performance.
Jack? So which GPU is this, NVIDIA?
Yeah, these numbers, I believe, were taken from Summit. So
if we go to like AMD or Intel, it might be different.
Yeah, that would be an interesting question. So these were all on NVIDIA GPUs. So it would be an interesting question if the
it's kind of benefit for CUDA.
And I could begin to answer that a little bit. So we have been targeting Frontier and Aurora as well. I would say that there are challenges mainly at the compiler level, but yeah, I don't really have a slide to address that here. So now putting on my kind of NERSC hat, I think from NERSC's point of view, we have this like common challenge with all of you, or like with the whole application community, which is as the HPC community kind of moves towards these energy efficient exascale like architectures, how do we make sure that the greater like scientific computing community doesn't get left behind? Because that's kind of what the whole point is. And so we've been thinking about this problem a lot for the last 5 to 10 years, which is how do we make sure that our diverse community at NERSC with roughly 700 different codes is able to run on these advanced architectures like the Cori KNL architecture and Perlmutter and beyond. And so this is the NERSC-specific roadmap where we, back in 2013, sort of started with the NERSC-7 Edison system, which was kind of beloved by users, but it really represented the end of a kind of multi-decade tradition of deploying HPC systems that basically all looked the same. They kind of had like a server-class CPU distributed across, like server-class CPUs distributed across many different nodes, connected by some, fancy high-speed interconnect. And every year, or every new generation, I think users could kind of move their code over to the new system without having to do anything and just get bigger, faster, better performance on the new system. This trend sort of ended when we brought in Cori, where we kind of realized if users did nothing, they might actually have worse performance on the new system than the old one. So there was lots of potential there, but you kind of had to work for it. And this was based on the Intel many-core CPUs. With Perlmutter, this is our first GPU system, and I think we think that trend continues. Like you have to put work into your code to get performance out of the GPUs. So when we were procuring Perlmutter, we kind of took stock of like what was the readiness level among applications for GPUs, and we found that it was kind of all over the map. So there were some applications that were GPU enabled already, based on past HPC systems like the Summit system at Oak Ridge. There were some that were kind of partially GPU ready. There were some that we knew could be GPU ready but weren't, because like a similar application was. And then there were some that were just like unlikely or sort of unknown. And so this is where we kind of started with the readiness process for Perlmutter back in the 2018 timeframe. Taking one step further back, though, I want to kind of go back to this plot here where we kind of started this process of moving people over to Cori. So if we were thinking about what was different to users about the change between the Edison system, which was deploying Intel Xeons of the Ivy Bridge generation, to Cori, which was deploying these Intel many-core processors. The code name there was Knight's Landing. Some of the big differences was in the parallelism per node. So one, we went from like 24 physical cores per node to 68. So that was a pretty significant difference. But maybe even more significant was how much parallelism there was in the core itself. So if you look at how many operations per cycle every core can do on that Ivy Bridge processor, it was 8. So you get that because there are 2 vector processing units for every core on a Xeon. And with the AVX2 instruction set, each cycle you can operate not on just a scalar, but actually a vector that is 4 double precision units wide. What happens with Knight's Landing is that goes up significantly to 32. You still have 2 vector processing units per Xeon. The vector width, though, actually doubles from 4 wide to 8 wide using the AVX 512 instruction set. And then you also have a new instruction called an FMA, which stands for a fused multiply add, which basically does a multiply and an add at the same time every cycle. So that's a pretty significant difference. And then the other significant difference was this addition of fast memory, which is similar to like the memory on a GPU. We went from 100 gigabytes per second of memory bandwidth available on Edison to like 4 or 5 times that of being available if you use the fastest tier of memory available on Cori. Then as we go to Perlmutter, this trend kind of continues. We get a lot more performance per node, and it's largely coming from these A100 GPUs. And if I go on to the next slide, you can see the difference in parallelism available. So if we take one of those sort of traditional Intel Xeon processors, this is the actual kind of traditional partition of Cori. You would have 64 cores per node across 2 different sockets, so each one has 32 cores. With hyper-threading, they could potentially support 2 threads each. With AVX2, you have 2 vector units that each support 4 double precision numbers. So you end up with 2,000-way parallelism when you multiply this together per node on this sort of more traditional CPU server class architecture. Now let's compare this to a GPU. So if we look at the A100s that are on Perlmutter, roughly the equivalent of a core is an SM, which stands for a streaming multiprocessor. It's not quite the same as a core, but let's just wave our hands for a second. It turns out that you can have up to 64 warps per SM active at a time. And a warp is essentially the same, roughly equivalent to like the vector unit of a CPU. And instead of being 4 wide, they're actually 32 wide. So it's like, instead of operating on a vector of 4 elements at a time, you're operating on a vector of 32 elements at a time. So if you do this math, you end up with 200,000 way parallelism is what you need for it to keep a GPU busy. And there is a little bit of hand waving here. I'm assuming that you want to oversubscribe the GPUs as much as possible to kind of hide latency, but that's how you end up with this 200,000. But even if you were not to do that, it would still be a significant difference. The other big difference between GPUs and CPUs is the fact that there are these different tiers of memory bandwidth. So if you look at a traditional Haswell Intel Xeon processor, you have about 100 gigabytes per second of memory bandwidth. Remember, on the KNL, I said you could get up to about 500. On the A100 GPUs, you can get 1,500 gigabytes a second from the HBM into like the processing elements. One complication, though, is at least on Perlmutter's architecture, the CPU and the GPU are connected via PCIe Express bus, and that has 32 gigabytes per second. So that's like a small pipe that leads to kind of connecting the two. But once you're on the GPU, you have access to very, very, very fast memory. And so, there's kind of a challenge here with just in the GPU picture that there are kind of multiple GPU optimization avenues. So you kind of need to think about how you get orders of magnitude more parallelism out of your application. You need to figure out how to best use the fast memory on the A1, like on the GPUs, but realize that moving the data back and forth between the GPU and the CPU is slow. And then there are even like other second order considerations. You want to make sure that the work that you're giving the GPU isn't so small that like the overhead of like launching the work onto the GPU dominates the time. And one of the things that the Labs team found out is that while the HBM memory is fast, keeping data in the caches on the GPU is even faster. And that was sort of one difference between the NVIDIA and the AMD GPUs. So,
One more question. Like the KNL architecture is much more similar to the classical CPUs. So
yeah,
from my personal experience, I feel that many people struggle to get their codes onto the KNL.
Yeah.
And it seems to be easier to get them onto the GPUs.
There is some truth to that. I would say the KNL is probably somewhere in between. I think I'm going to kind of go through a KNL case here in a minute too. I think in reality the KNL was maybe deceptive in the sense that you could take an existing code, you could compile it and run it, and that made it seem like it was deceptively simple. But the problem is, if you did that, you almost always got worse performance than you got on like a Xeon. And so the fact that it was so easy to get up and running, I think, sort of hid the fact that you still needed to put in work to actually rewrite your code. Where I think with GPUs, people are just have that mindset to begin with that, look, I'm going to have to do something to use the GPU. And so it might not be that it's like easier than KNL, it's just that it's more expected. It's like people's expectations were better aligned, I think. Yeah, so as we're thinking about this, like thinking about both moving our workload over to KNL and then moving our workload over to GPUs, a lot of the same questions come up. And I think some of the things we realized is that our code teams need a sense of absolute performance when optimizing applications. I've been to so many presentations and I've given presentations where somebody says, my code is 2 times faster today than it was last year, which is great in some sense, but it's also kind of meaningless because you don't know if the original code, was it like super slow, or is like the new code amazing because you're a ninja hacker? It's just, there's no sense of absolute performance there. And so I think like some of the questions that people answer is like, how do I know if my performance is actually good? And why am I not getting the peak performance advertised on the system? And maybe the most important question is like, how do I know when to stop? Like, how do I know when like it's good enough? Like, I could spend many, many more hours, but not get much more to show out of it. And then question 2 is what we discussed on the last slide, is that these new architectures have many potential optimization directions. And so how do you know which one to apply? Like somebody talked to you about a GPU and you realize, oh, it's great, vector processing power is amazing. But that might not actually be the thing that your code is limited by and would actually help your performance. And so we were thinking about these, and we were kind of thinking about this as a problem for NERSC to communicate to the user community at large. And we were thinking like, what could we tell the community? Optimizing their code for a new system is like, a staircase where you kind of do one step and then the next step kind of appears naturally and you just kind of continue progressing up and up. Or is this a labyrinth where you enter and never see the light of day again? Is it a space elevator where you just find like the right optimization for your code and you kind of rocket it up into space? And the analogy that we ended up settling on was the ant farm. And I like to say that this is the type of out-of-the-box thinking that gets you promoted at Berkeley. So, I guess the idea here is that there's sort of like always like these blades of grass that are sticking up. And, what you really need to do is just kind of continue running the lawnmower over them and cutting down the highest blades of grass to kind of figure out why is that piece sort of sticking out. And there are various things you can do with it. So we kind of turned this into like a flow chart. I'm going to talk about a couple steps and then how the roofline model will fit in here in a second. So one of the questions you might ask is, how do I know if I'm memory or compute bound for a given piece of my application, a given subroutine, or a given loop, or a given kernel? And there are actually some simple tests you can do. So one of the simplest things you can do is you can run your code twice using the same number of let's say MPI ranks or OpenMP threads or the equivalent of that. But in one case, spread them out twice as much as the other. So in one case, you would say run on a node using every single core. And in the other case, you'd run on 2 nodes using every second core. Yeah, so let's say physical cores. So forget about hyperthreading for now. So you just leave every second physical core free. And because memory bandwidth is essentially a shared resource, what this means is that every core has access to about twice as much memory bandwidth in that second case as the first case. So if you run faster in that second mode, where you're leaving every second core empty, what it likely means is that you're at least partially memory bandwidth bound. So this is kind of a simple test you can do, and you could run it like on, if you have enough timers in your code, you could figure out which sections of your code are sensitive to this test or not. Another test you could do is do that same sort of thing, add enough timers to your code, and run with simply varying the CPU frequency. So you can set the clock at its max value. So I think these are the Haswell numbers from Corey. And then you can just clock it down a little bit and see if you find that your code slows down. So if this is the case, then you are at least partially compute bound. And then maybe going to Volker's point that there's a third option. Actually, there's more than 3 options. But another thing that your code could be sensitive to is memory latency. And if you run with hyperthreading on, so this is where you would say run up to 4 tasks per core on like a KNL versus running with just 1 task per core. If this makes a difference, it's likely that you're latency bound. So by using hyperthreading, what you're doing is you're hiding latency by when one thread is basically stalled, you can context switch to the next thread. So these are kind of 3 really just cheap things you can do to kind of figure out what is limiting the performance of your application. It's not particularly sophisticated, but it led us to the conclusion that this performance model called the roofline model can tell you a lot of useful things about your application. And it's basically kind of taking the results of those last tests and kind of putting them on a plot that will help you guide your optimization for the next step. So who here has heard of the roofline model? So okay, so not very many. So the roofline model, I think, is a way to plot the application performance that you get in your application versus what you might expect from the characteristics of your like your loop or your kernel or your subroutine. And the reason why we like it is that it's actually just, there's nothing kind of unique about it. I think why it works is it's just pretty simple to wrap your head around. So what we have here is on the x-axis is your actual performance, or like the actual performance of a piece of code, which would be like a dot here, in terms of flops per second, or gigaflops per second, or megaflops per second. And on the x-axis is something that we call arithmetic intensity, which is the flops per byte that your code, that is the sort of the characteristic of your code. So what that means is how many flops is your block of code actually doing per byte that it needs to bring in from main memory or from some level of cache, right? So I'll explain this in a little bit in some examples in a minute. But these lines on the roofline curve are the maximum that you could possibly expect your code to perform given that characteristic. So let's go through how this looks in practice. So let me just say that the only thing I wanted to say about this slide is that there is a tool out here that will calculate these ceilings for you based on your architecture. So you can run it on, you could run it on your desktop, or you could run it on Perlmutter, and it'll draw these ceilings for you based on the specifications of the system. Okay, so let's look at these ceilings. So what this means is that if you go over to the right, you have a high arithmetic intensity. It means you do lots of flops per byte that you have to bring in. And so what that means is that the memory bandwidth of the system doesn't really matter, right? Because you're doing so much work on every little bit of data that you bring in that the cost of bringing it in is basically, well, washed away. And so that's where you can achieve the total peak performance of the system. So on KNL, that total peak performance was somewhere around like 2 teraflops, like 2,000 gigaflops per second. But it turns out that that's hidden, that in order to get that, you kind of have to do everything right. So you have to have nothing but FMA instructions. Like every operation you do has to be a multiply and an add at the same time in order to get that. You have to keep both of the VPUs busy. So if you don't do either of those two things, you're already down to this lower ceiling. Then remember that the KNL has 8 wide vector units. So your code has to be able to be vectorizable, or like the processor has to be able to operate on 8 numbers identically every cycle in order to get that performance. If you can't do that, then you're dropped all the way down here, another factor of 8 lower. And so like the scalar performance of a KNL is down at the 100 gigaflops per second level or lower if you're not doing all of those things right. Then if you're over here on this extreme on the left side, that means you have very few flops per each byte you have to bring in. And so what that means is it doesn't really matter what the compute characteristics of your application are. All that matters is how fast you can bring that data in. You're limited by the memory bandwidth, not the CPU frequency or anything like that. And so that's why you have these diagonal lines. The worse your arithmetic intensity, the more data you have to bring in per flop, the lower your kind of ceiling ends up being. And so these are why you have these diagonal lines whose position is based on the memory bandwidth. So with KNL, you have 2 different levels to the memory hierarchy. You have the high bandwidth memory, which is this ceiling here, and then you have this slower memory, the DDR, like the kind of traditional memory that is this ceiling here. And so that's why you end up being limited by a lower ceiling if you're running out of the DRAM versus running out of the HBM. So let's look at a couple examples. So let's say you then figure out, you plot the performance of your given application and you put its dot on the roofline curve. So if your dot is here, that means you have a memory bandwidth bound application, and you're essentially getting the DDR bandwidth. So you're probably not using HBM if you're on this line. On the other hand, if this is your dot, then you're likely have a memory bandwidth bound application, but at least you're using the MCD RAM to get higher memory bandwidth. If your dot is over here, well, good news, you have like a reasonably high arithmetic intensity. You're not moving all that much data, but you're probably not vectorizing or keeping both of those vector processors busy. The truth is that's usually a little bit more. It's usually more complicated. You won't probably be perfectly on any ceiling, but I think what we found is that asking the question of like, why am I not on a ceiling or why am I not higher, is always productive. It's always like the beginning of a good exercise to learning what's limiting the performance of your application. And there are many reasons why you might not be on a ceiling. It could be that you're not vectorizing. It could be that you have some sort of non-ideal task or thread scaling. It could be limited by communication and I/O. It could be memory latency. It could be a number of other reasons. But let's look at one particular example. So let's say you have this little application that's doing like a dot product. And let's just assume that here n and m are very large. By the way, I think this is some like sort of pseudo Fortran, but it's not actually legit Fortran. But anyway, I think you kind of get the point. So if you assume n and m are very large, such that these two big vectors, they don't fit into any level of cache, right? They have to come from main memory. Then during the execution, the number of loads from memory into like the compute registers is going to be n times m plus n, right? So every time you go through this inner loop, you have to read all of vector b, and you're going to do that n times. So that's where the n times m comes from. So this would be an example of an application so I say it requires 8 bytes loaded. So if these are double precision, it requires 8 bytes loaded from DRAM per FMA. So if you assume that you have about 100 gigabytes per second, like we have on Edison, then you could at most achieve 25 gigaflops per second with this application as written. And this is much lower than the peak performance advertised of Edison, which is 460 gigaflops per second. So this is an example of a loop that is memory bandwidth bound. So if I were to draw its position on the roof line, it would be way over here to the left, and probably like the dot would be right around that ceiling. So a trick to do this is something that you've probably heard of, which is called like blocking or tiling. So this is a common optimization strategy. Sometimes the compiler might actually do this for you. I wouldn't count on it. Lots of things prevent the compiler from doing things for you. But if we instead break this loop J, over J out, and we do it by blocks, such that each one of these blocks can fit into some lower level of cache, then instead of the amount of memory coming from DRAM being n times n, it would be n times m divided by the block size. If you kind of do that math. So the n times the block size is from doing this, the multiplication of these two inner loops. So the benefit is that you get to reuse this block size for all of the different n iterations. So what happens here is that you've moved your application from over here on the roof line to over here on the roof line. And now you have access to much higher ceilings by doing this optimization. And so this is something that we did in like a real application for Cori. Here's an application. This is actually one of the ECP applications called Warp. This now been renamed Warp X. But you can see they did a tiling optimization, which is sort of similar in spirit to this blocking optimization. And the before and after you can see is that they ended up moving significantly to the right and up in their roofline version. So the square here is the before and the triangle is after. We have some tools now available that give you all of this stuff for free. So you don't have to kind of run those little tests that I was talking about earlier. Instead, you could run Intel Advisor on an Intel CPU, or you can now run Insight Compute on NVIDIA GPUs, and they will give you these roofline plots for you. So this was created as a collaboration between NERSC and NVIDIA. And essentially what you have to do is, you load some modules, you run your application with this profiler, NCU, and then you use this flag set full. And then when you analyze the results, you now automatically get these roofline curves. So let me show you how we use this method to optimize Berkeley GW. So how am I doing on time? Okay. good. And feel free to interrupt me at any time if anybody has questions. This might be a good time to pause if anybody has questions.
I have a general question. You compared the AMD and NVIDIA GPUs, and you pointed out that there was like a smaller cache on the AMD, and certainly in the case of Snap, that cost us some performance. And I think it's true for other codes as well.
Yeah.
I was curious, like in hindsight, it seems like that was a mistake, and or was it just a natural thing they had to do because of various other constraints?
Yeah, I mean, I think it's probably something that they will rectify in the future. This is the honest answer is that NVIDIA has been doing like compute maybe longer than AMD has. So, both of the GPU designs started off as being designed for what does gaming need? What do we need for doing these specific processors or designing specific processors around gaming? Then early on, NVIDIA realized, well, these same processors that we've been developing for gaming could be used for accelerating other compute operations, specifically things that can vectorize well. And I think they just learned the workload before AMD did, but I think AMD has maybe learned its lesson now. In future versions, those cache sizes will be different.
So we can hope that in the future, maybe that will be less common to see things like that.
Yeah.
Everything will be perfect.
Right. That's perfect is always a dream world, but.
I just had a quick question on your example.
Uh-huh.
So for putting your program on the GPU, somehow adding additional for loop improves your efficiency, which is it's kind of against my intuition of what would happen. So could you elaborate a little bit more on why this actually happens?
Yeah, so is this example you're talking about? Yeah. So you're not really adding an additional for loop. What you're doing is you're breaking the J loop down, and you're doing it by chunks. So instead of doing J equals 1 to M, you're doing J equals 1 to M, but by blocks. And what's helping you out here is that each one of these, so this is like so J is some very, very long vector or an array, right? But the blocks are small enough that each of the blocks fit into some lower level of cache that's on either the CPU or the GPU, like either the L2 or the L1 cache, for example. And what that means is that for each of these, for each iteration of I from 1 to N, you don't have to go back out to memory to bring in this B array again, right? That B is just sitting there in cache, waiting to be used over and over and over again every time you change I. So that's the difference, is that B gets to stay in cache. You could, if you wanted to get crazy with the optimizations, you could do multiple levels of blocking, where you could do like blocking for the registers, blocking for the L1 cache, for the L2 cache, and beyond. But that's the benefit, is that you're improving what's called like the data locality, is that you get to reuse over and over again this block of B instead of bringing it in every time. Okay, so going to Berkeley GW example. So we're going to start off with KNL, and then we're going to move to the GPU. So there's this kernel in the Berkeley GW code called GPP, which stands for the General Plasmon Pole Approximation. It's not particularly important what it is, but this was sort of like the steps over time of us optimizing this code for KNL. And you can see that originally, as you were kind of pointing out, that when we first brought it to KNL, the first time we got it to compile and run, it was just like worse than the Xeon version by a pretty significant margin. So it was pretty disappointing. We got it up and running, but it was a lot slower. So here's some of the changes that we made. So the code is actually fairly simple. I mean, there's some simplifications that are hidden by this ... But But a couple of things that we changed immediately was we moved this loop, which went from 1 to 3, outside of being the innermost loop, because that prevented the compiler from vectorizing the code. It wouldn't vectorize the code when the innermost loop went only from 1 to 3, because it's like, that's going to end up being more expensive than not vectorizing it. So instead, we left this innermost loop being something much larger, something on the order of 1,000 to 10,000, where the compiler agreed that, yes, I'll vectorize this because it's big enough. Doing it by chunks of the vector width is better than just doing it serially. And then I want to talk about some other things that were in the code like this. We knew that certain combinations of the plane waves that make up the dielectric function would not contribute meaningfully to the final answer. So we had this cycle statement in there. And that makes sense if you're thinking serially, if you're thinking we want to save work for the processor by skipping some of these. But it doesn't make sense in a vector world where this just tells the compiler, don't vectorize it because not all the instructions are the same for each iteration of the loop. Like there's a fork in the middle of your loop where some values go one route, some values go another route. So this isn't good. This is sometimes in GPU world is called like divergence of your execution path. So what happened here when we did this step? So this is going from 2 to 3 when we made these changes that I'm talking about, reordering the loop, for example, and commenting out that cycle statement. We can actually show this on the roofline, which is kind of cool, right? So you go from 2 to 3. Our code vectorized, so it actually kind of went almost straight up in performance. So this was how it looked like on Haswell. On KNL, good news is the performance went up, like the overall flops per second went up, but everything moved to the left, which was not totally expected to us at the time. And you can actually see what happens if we run out of DDR versus running out of HBM. If we run out of the traditional memory, we actually hit the ceiling. If we run out of HBM, we don't yet hit the ceiling, but we're still pretty close. So what's actually happened is, if you look at this code, as we put the IW1 to 3 here, if we want to reuse all of these arrays, for IW1, for all of the IW values, it turns out that we would need 1,536 kilobytes of memory. Turns out, so the L2 cache on KNL is 512 kilobytes. The L2 cache on Haswell is 256 kilobytes. Unfortunately, both of these are too small to hold these arrays that would be useful to hold in memory for each of these IW to 1 to 3. On Haswell, though, there's this L3 cache that is big enough to hold these arrays that we could then reuse for each one of these middle loop values. So the fact that Haswell has an L3 cache, KNL doesn't have an L3 cache, is the explanation of why the curves went to the left on KNL, but didn't go to the left on Haswell, because the L3 was basically saving us on Haswell, wasn't saving us on KNL. So this is another answer to why KNL is sometimes harder to program than you might expect. So the fix here was we did exactly what I showed in that simple example. I just added a little level of blocking, which unfortunately makes the code a little bit harder to read, but fixes the performance. So now if we do it by blocks, where the blocks target the L2 cache on either architecture, this problem gets fixed, and you can see we move back to the right on the roofline plot for the KNL. Doesn't make much of a difference at all for Haswell because the L3 was always there to begin with. So the cache blocking optimization didn't really end up doing anything, but it was really important for the KNL.
I might be wrong, but I thought the latency of L3 cache was worse than L2 and L1, but does that not matter in this case?
It is, but in this case, it's fast enough in the Haswell case that it doesn't make a difference to performance. One thing I will show in a second is you can actually visualize that the roofline here, these bandwidths are the memory bandwidth limits, but you can also do roofline plots for cache bandwidths instead. Like the AI, when we say bytes per flop, you could say bytes from where, right? And the from where part could be L1, L2, or any level of cache. So actually, that's what is showing here. So if we break the roofline down and we provide a separate ceiling for each level of cache, you can see what's changed here. So in each of these plots, we have a ceiling and we have a dot for each level of the memory hierarchy. And so in the original code, you can see that there's this big gap here between the, what does it say? I guess the RAM and the like L1, L2, and MCD RAM. Whereas here, you can see that there's this split where the MCD RAM has kind of moved out to the right. So actually, I think to make sense of these plots, you should probably just ignore the red. The difference here is that all three of these plots, all three of these dots here are kind of on top of each other, where after the cache blocking, the MCD RAM dot has moved out. So that means we're getting better reuse of data out of MCD RAM because of the cache blocking we did to the lower level. Okay, and then there were some other things that we were able to discover, like the complex divides were generating non-vectorized instructions. So we were able to get some additional speedups from that are almost like pure vertical, and some additional speedups from also hyperthreading. So I think what is interesting is you can see this process kind of over time for both Haswell and KNL as it's improving. And one of the things that we did for Corey is we kind of had these plots for like all of the applications that we were looking at. And generally what you want to see is them going, well, definitely you want to see them going up because that's sort of the absolute performance. And often we want to see them going to the right as well.
So this is probably only a maybe code-specific comment, I don't know, but we actually were trapped with the FP model flag of the user compiler for a while before we realized it had been changed to something that wasn't precise.
I see, yeah.
So that flag, so what happened to us is that it worked practically always, except it would lead to sudden catastrophic computation errors.
Yeah, so that is a fair point. This flag could possibly be a little dangerous just to use at times. So I think you want to make sure that the code correctness isn't sacrificed either.
I don't know what to make of this, right? I saw that Intel did this. It's a good idea, but it was tricky.
In some cases, like the FP model has, I think, like 3 or 4 different versions, and you might have to tweak which one you use. In our case, the complex divides would basically be replaced by serial, so non-vector instructions by default. And with FP model fast equals 2, they're vectorized, but they're done via like an iterative method. And so there is some potential cases of risk, particularly if you have like a near 0/0 type situation, I think. But yeah, so anyway, that's a good point. Okay, yeah, so let's talk about GPUs next. So this is the same set of loops that we kind of had before. And we started looking at the performance on GPUs for different characteristics. So this loop is naturally 1 to 3. So just as a thought experiment, we kind of changed it from being 1 to 3 to 1 to n, where we could change the number of frequencies that we wanted to calculate the answer to. This actually happens in a different run mode for the code. And then the other experiment that we made is let's compile with and without FMAs, which also exist on the GPU, allowed versus disallowed in the compilation. So there's a few other things that we tried. So one was to change one of these loops over the plane waves to have a stride, just to see what effect adding a stride to the performance to the loops would have in terms of our absolute performance. And so here are some of the results. So this is again a hierarchical roofline. So there's a ceiling and a dot for each level of cache, from the HBM to the L2 and L1 cache on the GPUs. One thing that you can see is that as we increase NW, or the number of frequencies, we get better reuse of data, and we move from a data or memory bandwidth limited performance to something that's not memory bandwidth limited anymore. You can see that what's limiting the performance here is really the HBM speed. We're not really caching for any level like L2 or L1. Those are both much higher than their ceilings, whereas the dots are kind of right on the HBM dots are kind of right near their ceiling. Another interesting experiment then is what happens when we turn off FMAs. So the solid dots here are kind of the same curve with FMAs on. The hollow ones are without FMAs. And quite predictably, actually, we end up hitting that no FMA ceiling for what you could possibly expect the performance to be on the GPU. So that was good. Interestingly, we tried to sort of figure out what ceiling we should have based on the fraction of our operations that are FMAs, so these fuse, multiply, adds versus not. And you can see we're actually getting pretty close to that ceiling, but not quite. So there's some kind of gap that we don't fully have an explanation for, but it appears to be related to like some other non-floating point operations blocking how many FMAs we can execute per cycle. And then here is the effect of strides. So one thing that's really important to GPU performance is you have coalesced memory, or you're kind of accessing, each thread is kind of accessing the next value of an array in its memory access pattern. As we add strides, we kind of break that. And so you can see the stride 1 performance is always highest, stride 2 is lower, and then by the time you go to stride like 8, you end up being memory bandwidth bound again, because you're basically wasting 7 out of 8 of the data transfers that are being brought in. So this roofline curve can capture kind of like a memory coalescing issues as well. So this is sort of how we use the roofline model for Berkeley GW, and I think that it's kind of really, I don't know, I find it fun to look at these plots and especially watch how your application changes over time. But the idea is that you can really use the position of your actual performance on these plots to kind of navigate the type of optimization you should try. So if you're on one of these bandwidth ceilings, vectorizing your code isn't going to make any difference because you're limited by bandwidth, for example. and vice versa. If you're over here, you don't need to make a cache blocking optimization because you're not limited by bandwidth. A couple other suggestions I want to make just to the audience at a high level is that one of the things that has been really productive for us working with different application teams has been these hackathons. I know this workshop is going to kind of be hosting a hackathon in a few weeks. There's also this public series of hackathons, gpuhackathons.org, that you can sign up to join. They're kind of held all around the country, and actually all around the world, I should say, throughout the year. I think there's probably maybe like 20 events per year. And we often provide mentors to teams who apply. NVIDIA provides mentors to teams, and other facilities provide mentors to teams. And I think these events are really productive for maybe more sociological reasons than like technical reasons. I think there's something about like being in a room surrounded by other people kind of working on similar problems and like with experts kind of at hand, that's just kind of a contagious like environment for productivity. And so I highly recommend, taking use of these. They're free, and they can really help you focus on the code for a little while. As an example, I'll throw out this example with lamps and Xalt, where we hosted a few hackathons. But this is not a roofline curve, but it's just it's a curve that shows you the performance over time of the application. And I think you can see at some of these hackathons, you see like a week where you get almost near vertical improvement in your application as a function of time. And so this was a hackathon that was attended by like Aiden and some of Danny's team. And I think a lot of improvements were made through these events. And this kind of culminated in something that I think you heard about throughout this week already, which was this Gordon Bell submission that the LAMPS team, or like the LAMPS or Xalt team, put together in 2021. It was the Gordon Bell finalist. Largest MD calculation, I think, of this fidelity that had ever been done, up to 20 billion atoms. This plot down here is sort of interesting. It shows you the difference between the V100 performance on Summit versus the A100, or the next generation performance on Perlmutter and Selene. But this is not, I'll just say that this is one of kind of many that has come out of these type of collaborations. We've had the following Gordon Bell finalists since we sort of started doing NESAP 4 or 5 years ago, including some winners back in 2018, and a winner this year is again with the WarpX team. We actually had two. It's exciting. We had 2 finalists that were working with NESAP this year. Fortunately, only one could win, but this is one of the ECP applications, WarpX, in the accelerator physics domain. So I think I'll conclude there. So I hope I kind of convinced you that the roofline model can be a great way to kind of frame the conversation about application performance with like a science. For a science team, it's, I think, hopefully pretty easy to wrap your head around, but also useful and actionable. And one of the thing I want to mention is it's also available in a tool near you. So on CPUs, you can get the roofline plots right out of Intel Advisor, and on GPUs, you can get it right out of on NVIDIA GPUs, I should say, you can get it right out of the Insight tool. And then my last bit is consider joining hackathons, I think including the one that's going to be part of this workshop. And then any questions I can take.